let's talk about acid-base reactions. We talked about how we can predict products of a reaction by looking at the ions that came to the party and switching the partners and see if anything happens, right? We can use that strategy for precipitation reactions. It also works for acid-base reactions. So an acid-base reaction, which is also called a neutralization reaction, happens when you have an acid reacting with a base. The acid and the base neutralize each other, and they will produce generally water and some other soluble ionic compound. Another type of reaction we're going to look at in this section is the gas evolution reaction. And as the name suggests, a gas is evolved or produced during this reaction. You would observe that gas because there would be bubbling or fizzing. And that's the gas being formed, and it's less dense than the liquid, and so it comes and bubbles up and floats away. We talked about what an acid is when we learned about nomenclature. We said that acids are molecular compounds that form hydrogen ions when they're dissolved in water. And that's officially known as the Arrhenius definition of an acid. There's like 3 different definitions of acids. I don't care if you know the name of the definition, but you need to be able to identify this thing as an acid. And so what we're going to do here for acids is what we've been doing before. It starts with an H, and it's aqueous. So these acids ionize, they form ions when they get into solution. If you think about what is a hydrogen ion? Well, think about a hydrogen atom. How many protons? 1. How many electrons? 1. And no neutrons. It's just a proton and an electron. So here we have a hydrogen ion. How did it get to be a hydrogen ion? It lost its electron. A hydrogen ion is just a proton all by itself. Really small. Protons are not going to be hanging out alone in a solution. They're too small. I think of them as like newborn babies. When you see a baby, the baby is always with someone, right? A babysitter, mom or dad, brother. Somebody's holding the baby, somebody's taking care of the baby. Because the baby is too small to be out there by themselves. So hydrogen ion is too small to be out by himself. So what actually happens is this poor little hydrogen ion that's too small to be out by himself, he'll get a ride from water molecules. So the water molecule feels sorry for him and so picks him up. Oh, come on, honey, we'll take you with us. And so when you combine those two things together, you get the formula H3O+. It's going to look like this. It's like a water molecule with an extra hydrogen. But that extra hydrogen is just a proton with no extra electron, and so this has a positive charge. So this hydronium ion is actually what happens to those hydrogen ions that are produced by the acids. Most chemists use H+ and H3O+ interchangeably. Because if we use H3O+ all the time, then we're also going to have H2O in our chemical formulas, and we all just understand, well, of course the hydrogen ion is on a water molecule. It's simpler if we don't write hydronium. So you may see some equations where it has hydronium and some where it just has hydrogen ion, and they're both okay. We just know that the hydrogen ion is not actually by itself. So hydrogen ion is a proton. So we can have polyprotic acids many proton acids. That means they have more than one ionizable proton, more than one hydrogen ion that can come off. And those will come off sequentially, one at a time. There's only a few of those. Sulfuric acid is one of those, H2SO4. This has two hydrogen ions. It's called a diprotic acid because it has two protons that are ionizable. So H2SO4 can lose a hydrogen ion and form hydrogen sulfate ion. So that's one proton. And the hydrogen sulfate ion, so a base is a substance that produces hydroxide ion in solution. For the most part, these are going to be things like sodium hydroxide, a metal with a hydroxide ion, an ionic compound where we have a metal and hydroxide, and these ions separate when it's dissolved in water, so there's our hydroxide ion. The one thing that isn't like that we need to be aware of is ammonia. Ammonia is a base. It's kind of hard to recognize as a base because most bases have OH at the end. This one doesn't. What ammonia does is it will take a hydrogen ion from a water molecule. I guess we need to have H2O over here. So one of these hydrogen ions, those protons, will leave the water molecule and ride around on the ammonia, becoming ammonium. And then what's left when water loses a hydrogen ion? Hydroxide ion. So ammonia in water produces hydroxide ions. It is a base. Just like we had diprotic acids, some bases can produce more than 1 mole of hydroxide. So strontium hydroxide, there are 2 moles of hydroxide in every mole of this base. We don't have a special name for them though, not like dihydroxybase or anything like that. So in the neutralization, what happens is the hydrogen ion that came from the acid and the hydroxide ion that came from a base come together, and if you combine those, you get water, like down here. Hydrogen ion plus hydroxide ion gives us a water molecule. So this is an acid-base reaction. Here's our acid. We identify that because it starts with an H. Here's our base. It's a metal hydroxide. And what happens here is we're going to do that same partner swapping thing. So this would be H plus and Cl minus, Na plus and OH minus. And we're going to see, well, what happens if sodium and chloride get together? Well, when sodium and chloride get together, they form an aqueous ionic compound, so NaCl soluble. When hydrogen and hydroxide get together, they form water, a molecule, which is a liquid. So if we were to look at an ionic equation for this, these are both aqueous. We're going to separate those into ions. This is a liquid. We're not going to separate that one. This is aqueous, separate into ions. And then cross out the spectator.
I hope that hasn't happened to these folks here.
I don't think it's happened. Okay, so here are some common acids and bases. Compared to all the ionic compounds, there really aren't that many acids and bases in general chemistry. So here we have hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric acid. Those guys should be kind of familiar to you. Those are the 6 strong acids. There's only 6 of them, and so we need to just remember those. HCl, HBr, HI. Those are the ones in group 7 there. And then we've got nitric, sulfuric, and perchloric. You just kind of have to memorize those. Any other acid that you come across is a weak acid. So here's hydrofluoric acid, HF. And you might think, well, HF, why isn't that strong like HCl and HBr? Well, let's think about fluorine, chlorine, bromine, iodine. They're all in the same family, right? But who's the smallest one? Fluorine is the smallest one. When fluorine makes an acid, I think of it as fluorine's too small to be strong. So HF is a weak acid. The rest of them are strong, but HF is a weak acid. And then these guys. So this one, you may not recognize, but you should. If we cover up the H, C2H3O2 is acetate. Acetate ion. We put a hydrogen on there, we change the 8 to ic, and we have acetic acid. That's the acid that's in vinegar. But we can identify this because it starts with H. We know it's a weak acid because it's not one of those. Here's another one, formic acid. You don't need to know the formula or name of that, but we should be able to identify it as an acid because it starts with H, right? It's not one of the strong ones, so it's a weak acid. For the bases, we're mostly just going to see things like this, metal hydroxides. Those are all going to be strong bases. They're going to ionize completely. There's one weak base you need to be aware of, and that's ammonia. So let's write some equations here.
Another question is,
Mm-hmm.
I've noticed that acids tend to be rather small molecules, they're not really big. Is there any reason for that?
Yeah, acids are generally small, but there are large acids as well. Really large molecules like proteins and stuff, they're very hard to determine the chemical formulas, and so we don't really deal with them. If you want to deal with larger molecules, you'd probably be into biochemistry.
Okay.
So write a molecular and net ionic equation for the reaction that occurs between aqueous HBr and aqueous LiOH. We should recognize that this is an acid and this is a base. So we're going to write these down. HBr, we're told that it's aqueous, and LiOH, they tell us it's aqueous. How do we predict the products? We think about the pairs of ions going to a party and mingling, possibly swapping partners. So HBr is going to make hydrogen ions and bromide ions. Lithium hydroxide has lithium ions and hydroxide ions. And then if we swap partners, remembering we have to have a positive with a negative, positive and negative, positive and negative. And we go over here. We always write the positive one first. So we could have Li plus with Br minus, and we could have H plus with OH minus. Usually there's not going to be a precipitation in here. Is lithium bromide soluble? Yeah, lithium is that first row, right? Lithium, sodium, potassium, ammonium, they're all soluble. So this is going to be soluble, and I can write its formula. There's a +1 and a -1, and so that's going to be aqueous. And then there's this one, which, maybe your brain is in low gear, and so you're just kind of chugging along, and you say, well, it's a +1 and a -1. I just put them together. That looks weird. What is it? It's H2O, right? So instead of writing it like that, we write H2O. And what's the state of H2O? Liquid. So that's the molecular equation. Yes?
Does it matter the order you write it in? So if you wrote
No.
H2O first?
It doesn't. You can write the H2O first and the LIBR second. It's just like adding, right? 2 plus 3 is 5. 3 plus 2, also 5. Yeah. So it doesn't matter. And mastering chemistry isn't going to care either. It's at least that smart. Net ionic equation. Well, we kind of have some things down here that can help us. Are any of these not split into ions for the ionic equations? The water, right? So we don't want to look at that as split up. But these are aqueous, 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 so we're looking at the ions. Which of these ions didn't get involved? Did lithium get into a relationship? No. She maybe went home with bromide, but they're not like getting married or anything. They just got left behind. So lithium and lithium. How about bromide? Bromide shows up as an ion over here as well. So those are our two spectators. So we're going to end up with this very familiar equation here.
Thank you. I was like looking at it.
Yeah, it's getting a little warm in here. Any questions? If you're too warm with your space heater, feel free to turn it off. It's like 24 Celsius in here, almost 25. It's a little bit warm.
Okay. Quick question now
Yeah.
for you. Do you talk in Celsius or do you talk in Fahrenheit? Or do you just say that for the sake of chemistry?
I don't think of temperatures like the room temperature. I usually would think of, weather temperatures as Fahrenheit.
Okay.
But the thermometer that's in front of my face is 24.8 Celsius.
Okay.
And I can't convert that directly, but I can tell you that's in the 70s.
Okay.
It's like 75 or something. It's a little warm if you're dressed for winter. Okay, here's another one. Write the net ionic equation for the reaction between aqueous HCHO2, a weak acid, and aqueous NaOH. So here they're telling us it's a weak acid. So we need to consider that when we write the ionic equation. So it's asking for the net ionic equation, but we need to start with at least the bones of a molecular equation. So our acid is HCHO2, and it's reacting with sodium hydroxide. So again, to predict the products, we're going to take these apart into ions. This weak acid does form ions. It just only does that a little bit. But the ions it would form would be H+. There's one H here, right? So that's going to come off. And then what's left is the rest of it, CHO2. And we can figure out that that must have a -1 charge. That happens to be the formate ion. I don't expect you to know that. Sodium hydroxide. We have sodium ions and hydroxide ions. And then we're going to swap partners and see what happens. I'm going to draw the water first this time just because. So we put H+ and OH- together. And we're going to have Na+ and CHO2-. So hydrogen ion and hydroxide ion are going to form water. And what would these two guys form? +1 charge, -1 charge. It doesn't mean that you haven't, it doesn't matter that you haven't dealt with that particular ion before. it just is going to follow the rules. And so that's going to be NaCHO2. Sodium compounds, always soluble. That one's aqueous. We didn't have to, but we just wrote the molecular equation. So for the net ionic equation, we're going to split aqueous things into separate ions. The only exception is weak acids. Do we have a weak acid? We do. And it said this is a weak acid, right? So this is a weak acid. So what that means is that most of that is molecules floating around in the water. A few of those come apart into ions. So we're going to write that one together. And then the other one would be this liquid. That's not aqueous. We're not going to separate that. So we've got this guy and these ions and that guy and these ions. Are there any ions that are the same on both sides? Sodium. So sodium was just watching. So we crossed out the sodiums. There's nothing else we can cross out. And so HCHO2 plus OH minus is going to form H2O liquid plus CHO2 minus aqueous. And that's the net ionic equation. You're going to get a lot of practice with this on the pre-lab for experiment 5A. And you're probably going to make a bunch of mistakes, because that's how you learn. If you've ever been around babies, do babies fall when they learn how to walk? Yeah, at the beginning they fall more than they're up, right? Does it bother them? No, it's just part of life, right? So learning chemistry, you're going to mess up. I expect that. You're going to be confused. So what do? You ask questions, and that's how you learn.
Or in a baby's case, it tastes everything.
Yeah, babies do like to taste things, don't they? Okay, you've probably heard of an acid-base titration. So titration is a technique. It's not always done with acids and bases, but it often is. And what we're doing here is we're taking a substance in a solution where we know the concentration, and we're going to react it with another substance where we don't know the concentration, the goal being to find the unknown concentration. So we take the one solution and we add it to the other until we get stoichiometric amounts. The hard part is, how do we know when that happens? But that's called the equivalence point, when we've got equivalent amounts of both reactants. And then we can calculate the unknown concentration using solution stoichiometry, which we learned about recently. For acid-base reactions, the acid and the base, the reactants are colorless, and the products are generally colorless. And so we can't tell when we get to that equivalence point. So we use something called an indicator, which is usually an organic acid of some kind that changes color when the hydrogen ion shifts. So it might be colorless in an acidic solution and bright pink in a basic solution. And so when that changes color, that tells us, oh, you got there. So when we're doing an acid-base titration, and we get to that equivalence point, the moles of hydrogen will be equal to the moles of hydroxide. Pictures. So here we have the base in the burette, which is typical. And here's an Erlenmeyer flask. This should look a little familiar from that titration apparatus that you drew a picture of. So we've got the acid in here, and we've got the base up there. And we're going to add the base to the acid, and these hydroxide ions from the base react with the hydrogen ions of the acid and form water molecules. They neutralize each other. And so we keep going. We have an indicator in here. So when we get to just the right number, so they all match up, it's going to turn pink. Actually, what happens is you go a teeny tiny bit past, but it's so teeny tiny that we can ignore it. So this is what it would look like photographed. So initially it looks like you're adding water to water. Partway through, what you'll start to see is a little bit of pink here, because as the sodium hydroxide hits the middle, it's locally concentrated. And then when you swirl it, it mixes and finishes reacting, and the pink goes away. And the end point is when it stays pink. This one has been overshot. We want the first permanent pink. We don't want it to be bright pink. And that happens to be one of my favorite colors. Phenolphthalein pink.
What?
Well, that's what it is. Okay. A titration of a 20 ml sample of an H2SO4 solution of unknown concentration required 22.87 milliliters of a 0.158 molar KOH solution. To reach the equivalence point, what is the concentration of the unknown H2SO4 solution? Blah! Right? Oh my goodness. Can we go back to those cute pictures? What the heck? Okay, take a deep breath. We can do this. So, yeah, I read through it really fast. We're running out of time. So, you read through it, you go back, highlight the numbers, right? So I've got 20 milliliters, and I've got 22.7 milliliters, and I have a concentration. Those are all the numbers. And then I'm going to look for the question words. What is the concentration? So we're looking for the concentration of H2SO4. This is a stoichiometry problem. But they didn't give us a chemical equation, because we just learned how to write the chemical equations. So now they're just going to tell us what the acid and the base are, and then we have to write the equation. Well, we've got H2SO4. And we have KOH. How do we predict the products? We swap ions. So H2SO4 is going to have hydrogen ions and sulfate ions. KOH is going to be K plus and OH minus. And then we're going to swap partners. We'll get H plus with OH minus. And we'll get, no, it's not Na, it's K. K plus with SO4, 2 minus. This is like what we were just doing. Just ignore all the words at the top right now. So this is water, right? H2O. It's a liquid. And what's the formula for this compound? K2SO4. This is a -2 charge. We need 2 of these. So we've got our products, and then we need to make sure this equation is balanced. If you want to, you can use these little guys down here. We just need to make sure that we've got everybody represented. Because in this one, there's 1 sulfate and there's 2 hydrogens, right? And this is a K and an OH as H2O. Over here, K2SO4. So there's 2 of those K pluses and an SO4. So if I start over here and I'm looking for the hydrogens, I've got 2 hydrogens here. We could count this hydrogen. But then things get kind of weird. So maybe let's not start with hydrogen. Maybe let's start at the end of it. Let's start over here and look at sulfate. There's one sulfate on this side, and there's one sulfate on that side, so that's good. How many potassiums on this side? There's 2. How many on this side? Only 1. So that means I must need 2 moles of potassium hydroxide. So my sulfates are good, my potassiums are good. What about the hydroxides? I need another one over here, right? 2. And that means I need to have 2 H pluses as well. And then H plus, there's 2 of them here and 2 of them here. The water is a molecule in solution, but we can think of it as H plus and OH minus when we're balancing an equation. We just don't write it that way in an ionic equation. Okay, so good news. Most stoichiometry problems, they're going to give you the chemical equation. So it would just look like this. So we're going to use the equation to organize the numbers. 20 milliliters of H2SO4. So 20 milliliters of that. And 22.87 milliliters of KOH. And then this is the concentration of the KOH. 0.158 moles per liter. And then what they want is they want the concentration of H2SO4. So we have amounts of stuff, we have a chemical reaction, this is stoichiometry, grams to moles to moles to grams. Well, do we have a mass to start with? No. This is the one we know about, and this is the one we're trying to find out about. They gave us the volume. So they gave us milliliters. Can we go directly from milliliters to moles without kind of jumping through hoops? This gives us the relationship between moles and liters, right? So milliliters to liters to moles be the most straightforward, a little longer, but we're not going to get lost. Oh, what happened to my grams at the end? Must have accidentally erased that. Now at the end, are we looking for a mass? No. We don't want that. What are we trying to find? Moles per liter. So what if we stop this at moles? And then we know this volume, we can convert that to liters and find the molarity. So 22.87 milliliters. I'm going to convert that to liters. I'm going to convert that to moles of KOH. I'm going to convert that to moles of H2SO4. And then I'm going to stop there. So liters and moles of KOH. Milli means times 10 to the negative 3. Moles of KOH per liter. That's this guy right here. 0.158 moles per liter. Mole ratio from our equation. 1 mole of sulfuric acid to 2 moles of potassium hydroxide. (22.87 times 1 EE minus 3 times 0.158 divided by 2. And we've got 3 sig figs. I'm going to keep 2 extras. That's the number of moles of H2SO4 that were in this reaction. And this here is saying that the sample of H2SO4 had a volume of 20 milliliters. Well, 20 milliliters is going to be 0.0220 liters. The 2s are having babies or something. I don't know. It was just this one thing at the beginning that I did wrong. This is a 20, not a 22.
I was just gonna ask.
0.90336 or 0.0903 moles per liter is the concentration. We'll do a lot of stoichiometry titration calculations in lab. There will be some on exams, but we need to be able to do this in lab for sure. With a lot of practice.